Just going to look at stochastic computing integrators just to make sure we're all on the same wavelength, if you will. So we have this paper from 2017, hardware ODE solvers using stochastic circuits. And they do some pretty amazing things. Just as a quick review, so we're all on the same page. So if we want to encode a binary weighted number, or a number range, let's keep it simple, from 0 to 3, right? We put this number in binary weighted format here, and you compare it to a random number generator of equal width. So in this case, 2 bits, right? Because we want to be able to encode 0, 1, 2, and 3, right? So the random number generator is longer than that, but you only compare like the last 2 bits. So if the random number generator is less than the number in question, right, you get a 0, otherwise you get 1. Maybe I have that backwards, but that's how you're doing that. So now how does the integrate work? Well, everything is a 1 or a 0 in a digital stream, but the meaning is different now. Rather than taking a binary number in parallel, like let's say 3, so that would be 1, 1. And if you put that in series and it was still binary weighted, it would still be, 1 following 1. But stochastic encodes the number of into a probability sequence. So if you have the number 1 and you want to encode it in the minimum amount of space, you need 4 time slots, right? Because in 4 time slots, you'd have on average 3 zeros and 1 1 in any order, right? If I wanted to encode the number 2, I would have 2 1s and 2 zeros coming after each other, in any random order. And the number 3 would be, I'd have to have 3 1s in that sequence, right? Because so really you just count the number of 1s, and then you can scale it to the probability. But so it makes integration easy, so that if something's a 1, you just up count. There's the rules for the integrator here, right? So if you're supposed to decrement, like you have a negative number coming in, then it will take it down. So the counter takes this serial stochastic input and just has a memory of how many 1s there are. So it's converting it back to binary weighted, right? And this is like the state of the integrator. Then you take another random number generator, put it in a sequential thing, so that then you have a pseudo-random sequence coming out for whatever else you want to do. All right. This isn't meant to be an in-depth tutorial on stochastic computing. I'm just bringing it up to speed so we can talk about what I think these stochastic integrators are doing. So sometimes I like to see things visually. So here's a stochastic integrator. We set up our definitions and import everything. And here's my definition of an integrator. We have A, B, and the old state, right? And here is, we're only going to increment, right, just to test out the concept. But here, if A is 1 and B is 0, we're going to increment up, right? You could make a resettable integrator really right here by saying if I is greater than some number, go back to 0, right? Which a resettable integrator is It's like an integrate and fire neuron. A leaky integrate and fire, you would have to have something where if nothing changed, it would leak over time. All right, so this is, let's see if I can zoom in a bit here. Okay, so I made a fake pseudo-random bit stream. So all I'm trying to do is encode the number 1 in a system that can encode 0, 1, 2, and 3. So that means I need 4 times, right? So the first one, I have the 1 come first. So 1, 0, 0. That's 1 encoded into a pseudo-random bit stream. Then I have 0, 1, 0, 0. Then the next one, the 1 is delayed, and I just did that and then I repeated it. And so this isn't truly random, but the idea is that 1 can come anywhere every 4 time slots. Now, in a true pseudo-random thing, sometimes the 1 wouldn't appear. But on average, or if you go long enough, you'll get 1 out of 4. Right? You'll get 1 every 4 times. I just set everything to 0. I was having trouble thinking. That's okay. And so I just have my stochastic integrator equal to that, and I go through. Then something here is it's about, this is our discussion, like when is the data valid? And so I sample the array once every 4, because what I'm doing here is I'm taking 4 stochastic clock cycles to encode the number. And so every 4, there's a that you could say is another clock, and I just happen to be keeping the input the same. But every 4 clocks, right? Every 4, like you can't change the input less than every 4. All right. So this would be, according to my um, definition, is I have a clock doing all of this, but this S, right? I have to hold it for 4 stochastic clock cycles, because if I change it in between, I really haven't encoded everything. Right? I haven't encoded that number, or there'll be a number that it's not quite valid. Now you probably could get away with it, changing it whenever you want, but I guess my thinking is rigid. All right, so we come back here. So we have, this is all the number 1, and this is all the ways you can have number 1 encoded stochastically. Now, if it was random, the 1s would appear wherever. Okay. I've made it so it perfectly appears once every 4 clock cycles. All right. So the thing is what I'm saying is it's not really valid for every stochastic clock cycle, is that you have to sample it at the same rate that the data was put in, which is 4 times slower than the stochastic. So anyway, here is, let's see if I can zoom out a bit. So what we have here is the output of the stochastic integrator array at every clock cycle. Right. So this has the stochastic clock, which is 4 times faster than the input. So this clock cycles is a stochastic clock cycle, and I didn't really do the input very well, but you can see it starts off 1, 0, 0, then the 1 is delayed, then you have back to back, but right, and you can see that it integrates every time there's a 1, it goes up. Now here's the thing, we're integrating 1. Well, integrating 1, which is effectively integrating a step function. I'm just not showing time before 0. But you integrate 1, you get a constant called time, right? And it's just the slope is 1. So if you look here, the slope is jagged, that's not a line, it does approach, let's say, the function t, but notice I have 32 clock cycles here where it's always, it might be changing, but it integrates, it increments 1 every 4. And notice this, it goes from 0 to 8, and this goes from 0 to 31. And so, yeah, the slope of this line is off. It's not 1, right? If it was t, right, the slope of that line would be the exact number of clock cycles. So what I did is I sampled, starting at the fourth clock, stochastic clock, I sampled at every 4. So I don't start at 0. I start at 0, 1, 2, 3, in the index, and then every 4. And so then when you plot that, well, here's the one that was getting encoded every time, right? And then here's the integrator out. And yes, it starts at 1. That's just how it works. But notice it's a perfectly straight line. So what I'd say, get that yes, this is approaching, it's heading towards um, the function t, right? Really ramp t. Um, but it's, these intermediate states aren't useful to us. So I have to sample it back out, and now there is my function. And if you read that paper, they're talking about how you can make function generators. So yes, if I want to make I'm just gonna try some code here, see if it works or not. I want to make a sawtooth. Let's see, if I is, I don't know, greater than or equal to 3. I equals 0. Okay. So what this should do is whenever it goes over a certain value, it should reset. All right. So you can see when it goes over, but it looks more like a square wave generator, right? But when I sample it properly, yeah, it's looking more sawtooth. It's the time step isn't quite right, so you're not really getting the sawtooth. You're getting sawtooth-ish, right? So you have these numbers, which then can be used, in a function generator. So very simple function generator that can be created. But notice, if I don't sample it, like let's say I want to make a sawtooth or a triangle wave, right? I put this in and it's like a square wave, right? But by properly sampling it, I'm getting what I want. So that's my opinion, um, if you will, of how these things are working. Enjoy.